Yeah, my name is Leo. I'm going to talk about powdr, which is a toolkit that helps people build zkVMs and make zk proofs for high-level programs as well as make custom VMs. So to give some context, I guess this is a pretty specialized conference, but what does zkVM mean? So the term zero knowledge already doesn't necessarily make sense here because a lot of the zkVMs don't actually provide zero knowledge. What we're interested in is mostly the asynchronous part of this proof. So you want to prove that you ran a program over some data and you got some output and you want to send this proof to someone that you want to be convinced that you actually ran this program, the same program they think you did, and got the same output. And so the traditional way this has been done over the past years is with zk circuits, where they have a fixed size, fixed length, and you implement some business logic over some circuit, and the circuit gets the data, makes a proof, and is sent to the person. This has worked great, but there is a more scalable approach of doing that, which is over the past 2 years becoming more popular, which is the zkVMs, which in itself is kind of a circuit. Shares a lot of the properties as normal zk circuits because the zkVM itself is also a program. But instead of taking data and then spitting out a proof, it takes data plus a program and then it runs that program inside of the circuit over that data, then collecting whatever happened in the execution of this program and making a proof for that. So the reason why we want to make zkVMs is that it basically scales these proofs to any program that compiles to that VM. So you immediately don't need, it might be good to use zkDSLs, but you don't actually need to use zkDSLs for a lot of other things, which you could be using existing code or existing libraries or languages that are more established that you're more used to. There are quite a few existing zkVMs already. The EVM was leading a lot of the development of zkVMs because of Ethereum L2s. There are also a couple zk-friendly VMs that are custom-made for a specific purpose, and there's also implementations of more established VMs such as RISC-V, LLVM, and WASM that allow you to make zk proofs for executions of these types of programs as well. And there are different ways to build these zkVMs. So a few of them, or maybe even most, they're built with handwritten circuits, the same way we'd write circuits before. And a few of these zkVMs, they go one level higher in the abstraction stack, where the circuit itself, the VM itself, is built still as a handwritten circuit, but it allows for general purpose programs as input to make zk proofs. The advantages of making custom zkVM implementations, which is still the way these VMs are written, it probably gives you better performance over the approach that I'm going to talk about. But probably the most important advantage is that that's actually what you can do right now with available tooling. That's what you've had over the past years, and if that's what you have, that's what you have to do. A few disadvantages that actually Misha already mentioned a few. It's hard to audit, it's hard to change. You have this handwritten circuit, it's pretty difficult to iterate on and prototype and write tests and all these kind of things. So it requires a bigger team, lots of effort to build, maintain, test, and this whole thing. And in many cases, they're also fixed to a single input front end and a single back end proof system. So a lot of frameworks that give you Halo 2 proofs, they only use Halo 2. Or a lot of frameworks that use Stark proofs, they only use Starks, and so on. This creates a lot of inflexibility, basically, and vendor lock-in that might be hard to get rid of. So powdr is basically presented as a toolkit where the analogy we usually make is that if you think about 30 years ago, 25, 30 years ago in the gaming industry, if you wrote a game, you had a bunch of assembly code that you had to write using specific assembly and specific instruction sets from specific platforms. So if you're developing for Atari and you want to ship your game in a different platform, you have to completely port your entire system, your entire code. You have to rewrite everything from scratch before shipping it in a different platform. And the way we see And this is basically how circuit development has been for ZK programs. And the world we envision with Powder is where you can just reuse the languages that you know, for example, here Rust as this, in this example, and using libraries that you already have, libraries that have been already written for a long time and audited and reused. And the way we see Powder is basically what LLVM does for traditional software development, where you have many front ends, you have many languages that compile to LLVM IR, so Rust, C++, all of these. And then you have a single compiler pipeline within LLVM, which applies a lot of compiler passes, optimization, static analysis, these kind of things. And at the end, it opens up again to multiple platforms. You can compile LLVM to RISC-V, to WASM, to x86, and so on. And similarly, with Powder, you can basically take any front-end VM that's implemented using the Powder language, and any program that compiles to such a VM becomes a possible front-end. You go through a single compiler pipeline, and then it opens up again to multiple backends, where each backend is a proof system, for example, Halo 2 and Starks. So what exactly is Powder? It's a compiler. It's a compiler that applies a stack of multiple things that allow you to define zkVMs and low-level coprocessors for different reasons. Why are we building a compiler? Well, because of the same reason we also use compilers in the non-ZK environment. It abstracts away all the low-level complexities and weird things you have to do and allows you to focus on what your application should be doing and abstracts away what your application should not be doing. It also allows for modular machines, and this is really important for reusability, for disability, and this kind of things, because you suddenly don't have to rewrite things anymore if other people have already written or audited different things. It also enables the usual compiler things like optimization, static analysis, potentially formal verification. And the main goal is to basically maximize developer experience, to bring the developer experience we have in the traditional software development context into the ZK environment without actually compromising any performance. And the consequences of doing this is that you basically get a system that's easy to build, to prototype, to test, to audit, which is all we want as developer experience. This is a basic diagram of what Powder as a tool looks like. Everything inside the sort of square is inside the compiler. So basically here as inputs we have many high-level languages such as C++, Go, Rust, JavaScript, Solidity. These are just examples. And the entry point into Powder is an intermediate language. So similarly to LLVM, there's an IR, which is the entry point where which is how the programs are given. But next to it, the VMs themselves are also written and specified in this language, which is Powder assembly. So it's the same level of abstraction of the language. And the compiler is given the VM specification and the program, and it starts the compilation process by compiling this Powder assembly part and then compiling it to PIL, which is a polynomial identity language, first invented by Jordi and the Polygon zkVM team, which we extended to fit more of our needs, which is a constraint language. There's no notion of programs anymore. It's just arithmetic constraints. And from these constraints, you basically go to different proof systems, such as Halo 2, eStark, and Supernova, actually. One really interesting thing from this pipeline is that at every single point here, you can stop, look at it, and start again. So every single intermediate artifact, so for example, the assembly program or the constraints, you can basically get it outside, you can look at it, everything's human readable, you can understand what it does, you can optimize it potentially with different tools, and then just give it back. And then the compiler will restart the pipeline from there. So for example, if you do this for assembly, it just restarts, goes to PIL, you can do the same thing for the constraints, give it back, and then it finally goes to the proof system of choice. Why would you ever use this? The two main use cases that may fit people in the audience are for zkVM builders, people that are building, for example, L2s or L3s, and they want to have some execution environment, such as ZK EVMs and other ones. It basically enables people to focus on the high-level architecture of the whole system, on the design of the VM, which must fit which smart contracts they want to support, and on the prover itself. So they don't have to care about anything in the entire compiler pipeline. which is what I think most L2s, L3 networks would wish they could do. So this just makes it really easy to prototype different VM implementations, for example, start testing them, integrate with the smart contract language of choice, and also focus on prover performance and integration. The other main use case is you don't care about any of that. You just want to make proofs for your existing programs written, for example, in Rust or Go, C++, whatever. In that way, in that context, Powdr basically works as a drop-in replacement for your compiler stack. So if you use Cargo LVM to compile your Rust programs, you give the Rust program, it gives you a binary, x86, for example, as an artifact. If you use Powdr, it basically gives you zkP as the artifact. And as an example, we wrote the RISC-V front end, which basically took 300 lines of Powdr code in assembly to specify most of the instructions that the RISC-V32 IMAC instruction subsets would need. And this basically allows us to compile Rust programs through LLVM into RISC-V assembly, from RISC-V assembly into Powdr assembly, and so on. And we're currently working on different VMs and architectures, for example, EVM, Valid, and WASM. Especially WASM and EVM are pretty important here because of use case, and Valid because of performance. And this is one example of what this pipeline looks like. So here we have Rust code that is computing a catch. It's computing a catch hack. You're basically proving that you know the pre-image of a hash. This is normal Rust code. You only have to say there's no STD. We use the tiny catch hack crate, which is a common crate in crates.io, which is no STD. We take the public challenge is here, the hash we want to prove we know the pre-image for. Here, this is the pre-image. We hash it inside the circuit. This doesn't really look like a circuit anymore. We hash it, we compare it to the public challenge, and then we're done. This gets compiled by LLVM into RISC-V assembly. So this assembly, the language itself is just AT&T assembly, looks like any normal assembly, where the instruction set used is RISC-V. So the functions come from RISC-V. It could be x86 and different things. This gets transpiled almost one-to-one to Powdr assembly, which I'm going to show you in detail soon. This is what a very basic implementation of a VM looks like in Powdr assembly. So you can see that it's very simple. This is how VMs are implemented. So there's no built-in VMs in Powdr. So Powdr itself is not a VM. It's a tool that you can use to write VMs. And what we envision is the ability of having a standard library of different VMs where you say, here's a program and I want to use RISC-V, or I want to use WASM, or I want to use EVM. And it just seemingly takes that as input, and then it just makes ZK proofs for that. So this is how we define a very simple VM, which even has dynamic jumps, which used to be a very complicated thing to do in fixed circuits, but now it's just not anymore. So here we have a basic program, our main function, and Powdr assembly has very few built-ins. There's no built-in functions, only language constructs to build your functions. So here in our main function, we have a label start. This just looks like normal assembly. And then we're calling a function instruction add. We're assigning it to a register A. We're asserting something over A, and then we jump back to the start. This is just a common way of linking programs with an infinite loop at the end. And this instruction add, it's not built in. There's nothing built in. We have to define instruction add, which here we define by basically delegating it to another machine. So this is the modularity that I was talking about. So if you have a different machine that is specialized to implement, to verify a certain behavior, we can audit it separately. We can have a standard library of different components that we can use in multiple machines, in multiple VMs. The other instructions are here, for example, just asserting the two numbers are the same. And here is how we jump, for example, to a dynamic address. We just say that an XPC is the thing that I'm saying it should jump to. And the last thing is the ability to just declare registers. So it's a very simple language, but at the same time extremely powerful, that lets you basically define any VM. This gets compiled to PIL, which is this polynomial identity language. And here there's only constraints. We don't have to fully understand this right now. I just wanted to show you more or less what it looks like. This gets technical, but the idea is that this this set of constraints basically must be true at all times for such an execution trace that is the witness that is computed and given to the prover. As I mentioned before, one of the main aspects of modularity and what the language allows us to do is having a standard library. And why do we want to have a standard library? We still want to have optimized things. And that was my point earlier with we don't have to compromise on performance. And yes, we're still writing lower level code, which is still higher level than circuits because it's still a DSL, in a way that actually allows us to reuse it in any other machine that's built in PIL or powdr assembly. So this is an example of a test suite from our standard library, where this is basically a machine that just tests the Poseidon low-level implementation, where you can see here I have a machine main. We instantiate a Poseidon low-level machine. We have an instruction that just delegates the computation to this Poseidon. And we here just basically call this function with a bunch of different inputs, and then we test the output. And this test is has the same test vectors from the Polygon zkVM implementation. And you can see here that we're basically using a machine Poseidon Goldilocks from the standard library. So you just have to use it. It has a very simple module import system like in Rust, and just makes it, just gives it really nice DevX. And this, I mean, the standard library is pretty small for now, but we'll always improve, increasing it. So for example, for now we have Poseidon implementations for Goldilocks and BN. It's important to optimize it for each field, and powdr supports multiple fields. And then there's a machine that does optimized shift operations and binary bitwise operations. And this is an example of what I personally consider even better DevX, where all these low-level optimized machines that are part of the standard library are actually exposed in Rust as well. So this is just Rust code that calls the Poseidon Goldilocks machine from the powdr library in Rust and uses this function to test the same test vectors. And that's as seamless as it is. You just use library. And on the right-hand side, you see this is an example of, there's a small Merkle tree library that I have that has a sponge hash function. And in order to, I still want to test it natively, right? I want to run it in x86. I want to say that it works. But I also want to make zk proofs for it with powdr. So this is the entire diff that I have to write in the library to make it work with both powdr and natively. So I just have a cargo feature called powdr, and if that feature is enabled, I basically invoke the powdr Poseidon function and make zk proofs for it. Otherwise, I just call the native Poseidon function from some crate and run it natively. And the reason for using the powdr library version is that this does not generate any Rust LLVM code, because things like catch-check and Merkle trees and all these kind of things are pretty expensive, or signatures. They're pretty expensive to doing native code. So if I use some Rust code for that and compile to LLVM and try to make a proof for it, it's going to be a massive execution trace. It's going to slow down prover time and so on. Whereas if I use an optimized lower level version, it's going to be way, way faster. And this is the point where we can maximize developer experience by keeping our crates like barely changed, only needing to change the entry points to the heavy functions, at the same time get the performance of a low-level handwritten function. And the other point that's very important when making proofs for such programs like in Rust is zk continuations, where these circuits still have a fixed size. These execution traces still have a fixed size. We didn't really get rid of that. But there are techniques to solve it. You basically, when you have a real long execution trace, which you do in Rust, so for example, a single ECDSA verification function call takes about 4.3 million cycles in RISC-V. And this is really big, but if you could still do it, and simple execution traces, if you split them in different chunks, you make different proofs for them, and then you recursively aggregate them into a single proof afterwards. What this enables us to do is just really, in my opinion, really crazy things, like basically implementing a zk EVM like this. I don't expect it to be able to read this code, but this is Rust code that basically imports the REVM crate. So REVM is a Rust EVM implementation that passes the Ethereum test suite. It's used in the Reth Ethereum client. And so here, all we're doing in this 50 lines of code is importing REVM, loading the bytecode from somewhere, loading some data from somewhere, and running REVM on the bytecode and the data and the context that we have. That's it. So basically, we get zk proofs for EVM execution just by importing a crate and running it. This is a level of developer experience that we're looking for. Some applications of these things are kind of obvious, like zk-RISC-V and zk-WASM, because this enables you to make zk proofs for programs that already exist, like I just showed. zkVM is still a pretty big use case. And the two main ways we see to achieve zkVM implementations using powdr is the first one I just showed with zk-RISC-V, and then using some existing implementation like REVM or EVM1 or even Gath. The other one is writing specialized and optimized zk-EVM, similarly to what we did with RISC-V, but then for the EVM. The other use cases are, for example, L1 data and arbitrary computation, which is kind of the opposite of what L2s are doing, because L2s care about, Ethereum L2s care about EVM execution, but not necessarily about L1 state. And a lot of use cases actually care about the L1 state, but not about EVM at all, Rust execution or Python or something. And there are also other zkVMs that are custom, for example, Valid or Maiden, that could also implement the VMs themselves in powdr assembly. To conclude, I just wanted to bring back my main point that the main thing that a compiler stack gives you is the fact that all features apply to all VMs. So currently we have this RISC-V and Valid front end, and a lot of the features that we're building, they're first integrated with that in mind. So continuations, recursive proofs, optimization, static analysis, low-level coprocessors that we can use in Rust, and having a module system, a standard library, continuations, and eStart, like multiple provers, all of them work automatically for every single VM that you tried to use, be it WASM or RISC-V, VM, and so on. So everything that's built for the compiler automatically scales to every single VM that you're using. So this is my main point from the compiler stack approach that I wanted to present today. Yeah, thank you.
Thank you very much for the talk. I think we have time for one, maybe two questions, if they are quick. Anyone wants to jump in? Yep.
Sounds awesome.
Hello. Just curious, the Stark you are using, is it like based on your some third-party libraries, or you guys write
the
yourself?
Stark prover?
Yeah.
So currently it's so the technique is the eStark, it's the same as the Polygon zk-EVM. But currently the integration we have is with the zk-VM from Eigenlabs. They have their own prover, which implements eStark. Basically, it's a Rust reimplementation of the Polygon zk-EVM eStark paper.
We have time for one more quick question. Yeah.
So if we use the zk-RISC-V and build the EVM on top of it, how do Powder Labs stack handle the I/O and the networking?
So that has to be handled outside. So when you use the compiler, you basically, so the compiler has automated witness generation, but that also relies on prover inputs and outside inputs. So basically you have to give a callback, and the callback itself can be STD, it doesn't have to be no STD. And this callback basically acts as the data query, something that, and then you can query network and query RPC, you can query storage, and then just basically give it as prover data or public data to the compiler via this callback.
Okay, I think that has to be it, sadly.
Thank you.
Thank you very much. Thank you very much.